Hey guys, this is Bill. Today I'm going through two very important concepts in statistics. They are hypothesis testing and confidence interval. These two concepts are actually the same in nature, so once you understand how to derive a test statistics, you should be able to do both of them. In this video, I'm going to show you how a test statistics for hypothesis testing is derived. First, let me write down the simplest form of test statistics. Square root of n multiply x bar minus mu divided by the square root of s square, where s square is actually the sample variance, alright? So, in order to understand how a test statistics is arrived, we need to know three distributions by heart. So they are normal distribution, chi-square distribution, and t-distributions. So for normal distribution, all we need to know is that there is a special case of normal distribution called standard normal, which has a mean of 0 and a standard deviation or a variance of 1. Alright. As for chi-square distribution, we need to know that the definition of chi-square is basically that given an x variable that follow a standard normal, then the square of x follow a chi-square distribution with a degree of freedom 1. However, if we sum up n of such square numbers, then given that all the xi's are actually iid, then you have a chi-square distribution with a degree of freedom n. Alright? As for t-distribution, it is built upon the definition of standard normal and chi-square. So let's assume that there's a variable follow a standard normal, and we call it y. Then there is another variable z that follow a chi-square distribution with a degree of freedom, let's call it df. Then y divided by the square root of z divided by its own degree of freedom follow a t-distribution that has a degree of freedom that is the same as the chi-square distribution, which is, not n, but df. Alright? So now that we are familiar with the three distributions, we can proceed to how to derive the test statistics. So on the right hand side, I actually wrote down the t-distribution statistics so as to refer to it later on. So we start with an assumption that x follow a normal distribution with mu being the mean, sigma square being the variance. Alright? So what we can do is that x bar, which is the mean of the n observations from the normal distribution, follow a normal distribution still, and the same mean mu. However, the variance becomes sigma square over n. And then x bar minus mu follow a normal distribution with 0 being the mean and sigma square over n being the variance. Alright? And then x bar minus mu divided by square root of sigma square divided by n, then follow a standard normal. So this statistic, which follow a standard normal, is exactly what we want as the numerator in a t-statistic. Alright, so now obviously we need to derive a statistic that follow a chi-square distribution. Alright, so for a chi-square distribution, we still start from the assumption that x follow a normal distribution with mu being the mean, sigma square being the variance. Then x minus mu divided by sigma follow a normal distribution, which is the standard normal, alright? Then the square of this expression follow a chi-square distribution with a degree of freedom 1. And if you have n of them sum up, then you have a chi-square distribution with a degree of freedom n, alright? So here is something to know about the degree of freedom. So degree of freedom is basically the number of variables that you have in an expression that are freely determined. So here you have n observations of xi, that's why you have n freely determined numbers. So the degree of freedom is n. However, if we replace mu with x bar, this statistic actually follow a chi-square distribution with a degree of freedom n minus 1. Why is that so? That is because when you replace your mu with x bar, then you realize that given the first n minus 1 observations with x bar, your last observation of xi is actually determined, alright? So only n minus 1 observations of xi are freely determined. So the degree of freedom now becomes n minus 1. Alright, so let's revisit the definition of t-distribution statistic. Remember that your chi-square distribution will be divided by its own degree of freedom. So here we need to divide this whole expression by its degree of freedom, which is n minus 1, alright? And we can also take out the constant term, which is sigma square, alright? This follows a chi-square distribution with a degree of freedom n minus 1 divided by its own degree of freedom n minus 1, alright? And you realize that these underlying terms are actually the sample variance. Sample variance divided by the population variance actually follow a chi-square distribution with a degree of freedom n minus 1 divided by n minus 1, alright? So this is exactly the denominator that we want to find in the t statistic, alright? So now we plug in the denominator and the numerator and we obtain this expression, alright? And this expression follow a t distribution with a degree of freedom n minus 1. So you realize that in this expression, the sigma square terms actually cancel out each other. So after some simplification, you get square root n multiply x bar minus mu divided by square root of the sample variance. And this follow a t distribution with a degree of freedom n minus 1. So we call this term the test statistic. In your null hypothesis, we often assume that mu takes a value of mu naught, alright? So if you plug in this mu naught value here, you get a value for the test statistic, which you can use to either reject or not reject h naught. And we also know that t distribution is actually symmetric, alright? You can either reject this null hypothesis from the left-hand side or the right-hand side. And we call these 2 points critical values, alright? So the critical value actually can be determined from the t distribution. And given that your confidence level of alpha, you can actually determine these two values. And on the left-hand side, you should take a negative value, while on the right-hand side, you should take a positive value. Okay? If the absolute value of your test statistic is larger than the absolute value of the critical value, which is a very extremely unlikely event, given that the h naught is true, then we can reject h naught, alright? And as for the confidence interval, these 2 points actually also serve as the confidence interval. So the confidence interval can be rewritten as x bar plus minus square root of the sample variance divided by the number of observations multiply the critical value.